What's up, everybody? Existential Crisis Hotline. And today I want to look at time travel. It's always one of my favorite stories, movies when I was growing up. I think the first time travel story I ever read, I guess it wasn't technically time travel, but it had to do with the perception of time. I wish I could remember what the book was called. I remember it was about this kid, and I'm pretty sure he had like a brother, like a twin brother maybe. And he went into this, like he discovered some kind of like shed or something. He would go into this shed, and I don't remember how he realized this, but somehow he realized when he would go in there and spend time in there, time would slow down. And so he'd come out and a bunch of time had gone by compared to how much time he experienced being in this shed, right? And time physically slowed down for him. So if he spent a day in there, only literally biologically a day would pass, but then on the outside it'd be 10 days or something, whatever it was. And so then he goes in there, and I don't really remember much of the details because it was so long ago when I watched it, but it was like he would go in there and work out and study stuff and basically accumulate all this information and skills and so forth. And that's literally all I remember. But I remember it really impacted me when I was a kid. And then I must have been around I don't know, maybe fourth grade. It's hard to remember. But then I'd spend time in the library in middle school looking up books on not just time travel, but all that kind of stuff, like relativity theory, things like that, like what I could understand with the vocabulary of the average middle schooler. And it's funny because I remember, I read a lot of stuff, and then when I was in high school, I was sitting in my friend's car one time, and I was talking to him about relativity theory, about time dilation, because that really fascinated me. That thought experiment where it's you have two twins, one gets on a rocket and travels away from the Earth at close to the speed of light, comes back. It's only been a month or whatever, but it's been 40 years on the Earth, and his twin is 40 years older. And I remember telling my friend about this. This is in high school. And he thought I was crazy. He was what are you talking about, dude? That's not real. And yeah, maybe it's not real, but I'm no, this is actual scientific theories. And he was no. He had never heard of it, I guess. I just remember that being really funny. So anyways, I really like time travel stuff. And even today, some of my favorite books to read are time travel, although I haven't really read anything or found anything new very recently that was really good. But I figured we could look at some stuff, and I can make some recommendations if you're interested in that kind of thing. And then I have some cool videos and different things to look at. But let me pop over here. I don't have my window capture done properly. Give me a second. I have to make a new one. Let's see, Chrome. So I always like to start at the fount of all knowledge and truth, which is Wikipedia, obviously. But I figure it's a good jumping off spot. I like the fact that you can click lots of blue links. Now, it says time travel is the hypothetical activity of traveling into the past or future. Oh, and at the end of the stream, I'll tell you about some time travel experiments that I've actually done myself successfully. So stick around for that. Anyway, so time travel is a concept in philosophy, space, time, and fiction, particularly science fiction. In fiction, time travel is typically achieved through the use of a device known as a time machine. The idea of a time machine was popularized by H.G. Wells' 1895 novel, The Time Machine, which I've read it, and maybe it was just such a new concept at the time, that's why people liked it, but I didn't really like that book too much. Although the movie that they made, I'm sure they've made multiple versions of it, but the one they did with, I think it was Guy Ritchie. Because remember, it's the same guy from Memento, I believe. Guy Pearce, not Guy Ritchie. What the hell? Guy Pearce. Guy Pearce. That'd be funny if it was Guy Ritchie. I don't even know who that is, actually. That guy. How do I know that guy's name? I've literally never watched anything he's done. Is this a famous person? Oh, Lock, Stock, and Two Smoking Barrels. Okay, yeah. I definitely watched that when I was younger. Although I don't recognize anything else. But yeah, I guess it's like a famous director. Okay, so not that one. Guy Pearce. This guy. He was in that movie Memento. Oh, well, that's not really about time travel. But Memento is about this guy who there's some kind of accident, like his wife is murdered, and then he also gets hurt in the process, and then he like has this condition. There's a name for it where you can't form new memories, so you can remember everything up to that point, but then he can't remember he can't form new memories. It has like sort of a 15-minute attention span or short-term memory, and then his memory resets and he like can't remember where he's at or what's going on or anything. And so he ends up tattooing clues because he's trying to solve his wife's murder. He ends up tattooing the clues that he would want to make sure like he knows for sure on his body. And so like, every so often his memory will reset and he'll look down and he'll be like looking at his body, his tattoos, and like piecing it together going like, okay, all right, this happened. I've got to find this person. Okay, contact so-and-so. So then, and it's actually a really cool movie because it's not really time travel, but it kind of gives you that same kind of feeling. Oh, I need to stretch this picture out. There we go. So it kind of gives you the same kind of vibe as like a time travel movie. But it's interesting too because like people start manipulating him because they know he has the condition, but he doesn't know they know, and he's got to like remind himself that this person knows, and it gets pretty wacky. So anyways, that guy was in this movie, The Time Machine, which I really liked it. And I remember reading the novel much later, the H.G. Wells novel, and it wasn't as intense as the movie. I was like, the movie was so much more crazy. There's this one scene in the movie where he goes really far in the future, and I don't remember the context of why, but like he looks at the moon and it's like split apart in multiple pieces, like some kind of accident happened and the moon is like, it's like fragmented up in the sky. I just remember being really, I was going to say freaked out. Not really freaked out. It was just like a weird feeling I had whenever I saw that in the movie. I don't know why. Maybe it's similar to how people get really freaked out over like watching an eclipse, which I haven't gotten freaked out about that personally, but maybe it's similar. Some people describe seeing eclipses as like a religious experience. So anyways, it's a pretty cool movie. I liked it. Yeah, so that's all I'll say about that book. I'm not saying it's not worth reading, but I think there's some much more interesting time travel novels. Actually, one cool thing about it though is like the guy invents this time travel, and I feel like they didn't do this in the movie though, at least that version of it. In the movie, I can't really remember what happens at the end, but in the book, it's like he's sitting around this table telling the story of how he created all this time travel, this device, and like the people are kind of skeptical, and yet there's like clues in the beginning that he actually did it. Like his clothes are torn. Like when he comes in to talk to them, he's like really tired, and so that all gets explained in the book. So it's not bad. It's not bad. It's uncertain whether time travel to the past would be physically possible. Uncertain. So it's not impossible. At least no one knows. Such travel, if at all feasible, may give rise to questions of causality. Forward time travel, outside the usual sense of the perception of time, is an extensively observed phenomenon as well understood within the framework of special relativity and general relativity. Forward time travel. That's just like Oh, maybe they mean like going into the future, not just like being alive. Like, isn't that just like normal? However, making one body advance or delay more than a few milliseconds compared to another body is not feasible. So it is possible for a few milliseconds? That's interesting. As for backward time travel, it's possible to find solutions in general relativity that allow for it, such as a rotating black hole. Traveling to an arbitrary point in space-time has very limited support in theoretical physics and is usually connected only with quantum mechanics or wormholes. History of the concept in religion. I never really considered that there would be time travel in different religions. Some ancient stories feature characters who appear to leap forward in time. Vishnu Purana, a Hindu mythology, narrate the myth of Raivata Kakudmi, who visits the god Brahma in heaven and returns to earth to find that many ages have passed. That's interesting. I was reading that book last night, Memoirs of My Nervous Illness by Daniel Schreiber. Or is it Paul Schreiber? Either way. And there's this part where he's like describing, it's such a weird book. It's so weird because it's so like clearly, lucidly written, and yet the guy is not skeptical about what he experienced. He's skeptical in a certain sense. Like, he'll say sometimes, he'll be like, I can't prove if this particular thing was a hallucination or not. I can't really rule it out. But this other thing definitely wasn't, and here's why I think that. And anyways, he was talking about this one period. He calls them calls it like the holy times. This period when he was in the mental asylum, where he thought for sure that like hundreds of years had passed, and it would only been like maybe a day. And he said at the time he couldn't look out the window, he couldn't see like things outside, maybe like buildings had decayed and collapsed outside. He would, how could he know? And he really thought that like hundreds of years had passed, and he was the only human being like left on Earth. And even the people he would interact with in the asylum, he called them, what does he call it? There's a name for it. He has like this fleeting something, like fleeting humans or something. There's some word he uses for it. They're people where they're not real people. They're just bodies that are animated by a miracle, he says. So his like mind went into all these different crazy areas. And there was one part where he described he's certain he wasn't hallucinating, where he could actually see two different suns, where there was like our normal sun, and then there was another one which he thought was a group of stars that had condensed to look like a sun. And crazy stuff. But it's really fascinating. Primarily because most of the schizophrenic writing that you might read or come across, like remember we did Francis E. Deck in a different live stream, it's so clearly schizophrenic. It's like all over the place. It doesn't even make coherent sense at all. But this is like somebody who, he was a lawyer and a judge, and he was relatively highly educated, and so he could write it all down. And I know I mentioned this before, but it's so funny because it's like it's really thick. It must be like 300-400 pages at least. And it's like he wrote it in a way to clarify everything he experienced, and he wanted to give it to the guy running the mental asylum to like prove that he was sane again. But he wasn't questioning anything that he experienced. He was like, no, it's like it really all happened, but I'm totally lucid now, but I also want to make sure that I get all this information out because it's all this religious, spiritual information. And it's also interesting because he didn't he didn't grow up as a very strong religious person. He didn't believe in God originally, and yet these experiences got him to believing in God, but not in the typical normal Christian sense of the culture he was that he was in. But it's so funny because at the beginning of the book, in the preface, he's like writing this letter as a preface to the guy who runs the asylum named Fleixig, and it's almost like he's trying to explain himself, and then at the end he's like, I'd like you to confirm the following, and it's this whole list of like, can you confirm that you were speaking to me telepathically? And there's like all this crazy shit. I'm like, dude, this is not helping your case at all. Anyways, in the Buddhist Pali Canon, the Payasi Sutta describes how the disciple Kumara Kassapa explains to a skeptic that time flows differently in the heavenly realms. Okay. The Japanese legend of Urashima Taro, first recorded in the Manyoshu, tells of a fisherman who visits an undersea place for 3 days only to return to find that centuries have passed and his world is gone. Okay, so forward time travel. Kind of same thing here in Judaism. And same thing it looks like in the Quran as well. It's all like they just went less time passed subjectively than outside. Time travel in science fiction. Time travel theories in science fiction and the media can be grouped into 3 categories. Immutable timeline, and alternate histories, which are less interesting to me personally. I don't really care about the alternate history stuff so much. It's always more interesting to me when people are traveling in time and then you have sort of like a looping effect. There's a lot of stories like that where it's like you start creating these consequences and it's like your whole reality starts unraveling because of the consequences that you create by going back in time and interfering with things. The non-scientific term timeline is often used to refer to all physical events in history, so that where events are changed, the time traveler is described as creating a new timeline. Sometimes. Oh, this is interesting. I haven't heard of some of these things. Early science fiction stories feature characters who sleep for years and awaken and they change society, or are transported to the past through supernatural means. So there's this book, The Year 2440, A Dream If Ever There Was One. Never heard of that. I wonder if it's any good. So it seems like he falls asleep and then wakes up in the future. Kind of interesting. Rip Van Winkle. I have heard that name before. Isn't that the guy from the Mary Tyler Moore Show? No, that's Dick Van Dyke. Same person, right? Rip Van Winkle. He imbibes a strong liquor and falls asleep. Awakes 20 years later. Well, that's not very interesting. 20 years. They're like, so much time has passed. What could change in 20 years back then? The revolution's already happened. Looking Backward by Edward Bellamy. A utopian sci-fi novel. In the 19th century, only Uncle Tom's Cabin sold more copies in its first years. Wow. Inspired several utopian communities. So the guy falls asleep in Boston in 1887 and then wakes up in the year 2000 in a socialist utopia. The problems include problems associated with capitalism. It's so interesting to me. Like, that's when was this written? 1888. It's so interesting because maybe not everyone thinks this way, but it just seems to me like all the criticisms of capitalism and all this stuff like that happened recently. And I think even people, when they think about communism, I know I did before I started studying things. Socialism, communism, I always imagined, and before I was educated on the point, that it just happened in like the 50s or something. And I think that's primarily because of the impulsing around the Cold War. And I don't know if this is a common thing that other people thought of it this way, if they haven't, like I said, been educated at all on it. But I always just kind of assumed that, oh yeah, communism was a thing that happened in like the 50s or 60s or something. But it goes all the way back to the 1800s at least. People were already, Marx was writing back then. He wasn't writing in the 50s. But because you're born in this period of time, the only way you know the past is through reading things from the past or your education, which frames things in a certain way. And I definitely don't remember in school learning much about communism, now that I think about it. Outside of the Cold War, like Vietnam, Cold War, that kind of stuff, and I went to a college prep school. We studied world history, U.S. history, which obviously there wouldn't be well, there's still a history of socialism and stuff in America, but I don't really ever recall studying any of it at all. Kind of weird. He predicted Costco and Sam's Club. Debit cards. Interesting. When the Sleeper Awakes by H.G. Wells. Prolonged sleep is used as a means of time travel in these stories. Okay. The date of the earliest work about backwards time travel is uncertain. The Chinese novel A Supplement to the Journey to the West by Dong Yue features magical mirrors and jade gateways that connect various points in time. Huh. The Monkey King is trapped in a dream world by the Kingfish Demon. Chingfish Demon? An embodiment of desire who wishes to eat his master, the Tang Sanzang. He wanders from one adventure to the next, using a magic tower of mirrors and a jade doorway to travel to different points in time. I feel like it wouldn't be very interesting to read, though. Especially when you have these translations of like really old texts. It's like reading the Odyssey or something. It's probably way better in the original. Dang. Let's see. Around 1640. That's interesting. There wasn't much stories about time travel before then, even the 1600s, which seems like a long time ago, but it's really not. I mean, when was the Odyssey written? I definitely spelled it wrong. Yeah, I spelled it wrong. 1D, 2 S's. The Odyssey. Mid 6th century, 7th or 8th century BC. So like 2,900 years ago, something, 2,800 years ago. No time travel in that, as far as I know. The time travel is taking place inside a illusory dream world created by the villain to distract and entrap him. Okay. Samuel Madden's Memoirs of the 20th Century is a series of letters from British ambassadors conveying the political and religious conditions of the future. Because the narrator receives these letters from his guardian angel, Paul Alcon suggests in his book Origins of Futuristic Fiction that the time travel in English literature is a guardian angel. Okay. In the science fiction anthology Far Boundaries, August, your version has a shit ton of time travel? Oh, you're talking about, I know what you're talking about. Talking about Ilium. Yeah, I know, that's why I hesitated when I said, or does, that I know of. Like, let's see. Where was I? Short story about time travel and anachronism or missing one's coach. Okay. Charles Dickens. A Christmas Carol. Oh yeah, I guess that is about time travel. Yeah, okay. Paris Before Min. The protagonist is transported to the prehistoric past by the magic of a lame demon. where he encounters a plesiosaur. That's boring to me, personally. Edward Everett Hale's Hands Off in 1881 tells the story of an unnamed being, possibly the soul of a person who has recently died, who interferes with Egyptian history by preventing Joseph's enslavement. Early time machines. One of the first stories to feature time travel by means of a machine, the clock that went backward. An unusual clock, when wound, runs backward and turns people nearby back in time. Enrique Gaspar y Rimbaud's El Anacrompete. The Time Ship. Wow, that's a word. A chrononautical journey. Es una novela de... No, I'm not doing that. I wonder if it's good. A satirical take on time travel. Starts in Paris, takes the reader to China, Pompeii, Mount Ararat, all the key moments in history. Some solutions to Einstein's equations for general relativity suggest that suitable geometries of space-time or specific types of motion in space might allow time travel into the past and future if these geometries or motions were possible. What do you mean by motions? Like if you wave your arms in a certain way? In technical papers, physicists discuss the possibility of closed time-like curves, which are world lines that form closed loops in space-time, allowing objects to return to their own past. Ooh, that sounds like Primer to me. There are known to be solutions to the equations of general relativity that describe space-times which contain closed-like time curves, such as Gödel's space-time, but the physical plausibility of these solutions is uncertain. Any theory that would allow backward time travel would introduce potential problems of causality. The classic example of a problem involving causality is the grandfather paradox, meaning you go back and you cause the death of one of your ancestors and then you're never born. Some physicists, such as Novikov and Deutsch, suggested that these sorts of temporal paradoxes can be avoided through the Novikov self-consistency principle, or a variation of the many worlds interpretation. What is this? If an event exists that would cause a paradox or any change to the past whatsoever, then the probability of that event is zero. Well, that means you wouldn't have free will. So... would that just mean the probability of time travel is zero? Because it creates possible paradoxes? Time travel to the past is theoretically possible in certain general relativity space-time geometries that permit traveling faster than the speed of light, such as cosmic strings, traversable wormholes, Alcubierre drives. Oh, it's so weird, because I was thinking... when it talked about, where was it? Traveling faster than the speed of light, it just made me think of Three Body Problem, which if you have not read Three Body Problem, it's so good. It's 3 books: Three Body Problem, Dark Forest, and Death's End, and they're really, really good. Super mind-bendy, physics-based, and I really like those books. But the reason I thought it was interesting is because when I clicked on this is described in that book. Spoiler alert. Contracts space in front of it and expanding space behind it. Okay, I'm going to try something here. Oops, that's not what I meant to do. Okay, I'm gonna ask ChatGPT, create a make no mistakes. Let's see what it does. What, a picture? Well, let's see what it gives us. It might give us a technical diagram we can use. Sketching it out, all right. Sketching out the Alcubierre drive. Making the first draft. Setting the scene. It's very helpful. Polishing the details. This is good. This is good. I feel like we're going to get something here. Finishing up. All right, here we go. Uh-oh. Look at that, guys. I just created a time travel machine with AI. The Alcubierre drive enables apparent superliminal travel by contracting space-time in front of a spacecraft and expanding it behind, creating a warp bubble. Space-time geometry, see the warp bubble? And then after the warp, energy density. Okay, so we get a little graph here. That's pretty good. It checks out. We got our key properties. No local violation of special relativity. That's key. Apparent faster than light by space-time manipulation. Requires exotic matter, of course. Ship remains in normal space-time. That's always good, too. Causality violations possible. Okay, so we got to kind of worry about that a little bit. Okay, that looks pretty good. Give me a technical schematic so I can build one. See what we get. Another picture. Okay, it's going to create another picture for us, but see how that goes. Okay, sketching it out. I'm glad that it tells me what it's doing. Okay, we got the first draft going. Do you think it actually makes a first draft and then like edits it and makes a final draft? I feel like it's just saying the same thing it said last time. I think this is just for entertainment purposes. I don't think it's actually doing any of those things. Although it did add some final touches this time. One last tweak. That better be the last one. No more tweaks after this. Come on. I might be overloading their servers with this. No one's ever done this before. There we go. All right. Okay. Yes. Let me zoom in because this, I might have just made history, guys. Hopefully you can see that. Take some notes. Okay, so we already know what it does. We've got the field projector. This is looking pretty good. Field projector array, typical module. We got the magnetic flux shaper, of course, the vacuum chamber, negative energy injector, superconducting magnet coils, the field emitter grid, the Casimir plate array. That's important. And the coolant lines, because you don't want it to overheat, obviously. Got the exotic matter system here. You can't see my mouse, that's okay. What else do we have? Components list, okay. Need to put that together to get at Lowe's later. Typical dimensions, 120 meters is the field. Damn. The ship is about 100 meters. That's pretty big. They're going to have to operate at cryogenic temperatures, it said. Okay. Power core must be isolated from the field projectors. Good. Okay. All right. Not possible with existing or near future technologies. Look at this warning here. Improper field configuration may cause catastrophic space-time instabilities. I'm okay with that. Okay. Give me a shopping list. for the parts. Searching the web. Searching for superconducting magnets, cryogenic equipment. I can't build it. I can get a $2,500 cryofab liquid helium system, cryotransfer suitcase package, a molecular pump, a superconductivity experiment for $7,500. I don't think this is going to work, guys. The large capacity cryogenic storage system is $48,000. What if I could finance that? So most of the stuff is real except for the exotic matter generator and the warp bubble generator and the faster than light propulsion. So pretty much the important stuff. Okay, maybe I need to try something a little bit rudimentary. It's a little too much. Create a schematic for the time travel machine from the movie Primer. It's a little bit more simplistic. I mean, they were able to build it in their garage with very rudimentary parts, so I would think that would be possible. It's sketching it out, of course, so I have to wait for that. I'm going to say the Alcubierre drive is not going to work, guys, unfortunately. We'll check back on ChatGPT in a bit. Stephen Hawking formulated the chronology protection conjecture, suggesting that the fundamental laws of nature prevent time travel. I don't want to hear that. Wormholes. A traversable wormhole. The Casimir effect shows that quantum field theory allows for the energy density in certain regions of space to be negative relative to the ordinary matter vacuum energy. But it has been shown theoretically that quantum field theory disallows states where energy can be arbitrarily negative for an arbitrary length of time. The quantum foam hypothesis. I feel like they're just making stuff up at this point. Let's see how we're doing with our time machine. Okay, now that's what I'm talking about. What do we got here? That can't be right, though, because it's very small. At the bottom it says, it's not possible, Aaron. This device is experimental and non-reversible. Use at your own risk. The machine does not travel to the future. It creates a new branch timeline. Original timeline. Branch. You cannot return to the original timeline. Well, that's not helpful. Okay. Let's go back to time travel in fiction. This is more interesting to me. A time slip. I was going to talk about that later. There's a Philip K. Dick novel called The Martian Time Slip. Time slip is one of the main plot devices of time travel stories, another being a time machine. Okay. So a time slip as opposed to a machine. That makes sense. The difference is that in time slip stories, the protagonist typically has no control and no understanding of the process, which is often never explained, and is either left marooned in the past or future time and must make the best out of it. Okay. We've got time portals. Ooh, this sounds interesting. An influential example of such a work is the short story By His Bootstraps by Robert A. Heinlein, which features a time gate built by aliens. I have never heard of that. I don't want to get a spoiler here. Common Sense under Heinlein's name. That's funny. So there's time portals, communication from the future. Just looking at that. A really good book for that is Timescape by Gregory Benford. That's a really good one. Is this the one I'm thinking of? Earth is falling apart. Yeah. It's like this physicist in the 60s. He's doing these experiments with tachyons. And then his experiments, like, I forget what it is. They're measuring something. And then he notices that there's like some kind of pattern in his experiment in the results. And then he starts realizing it's like a message. And it's like a message from the future where they're sending back these transmissions because there was some kind of problem in the future that they were trying to get them to correct in the past. And one of the interesting ideas in it is that the scientists in the future, they are shooting the messages off into outer space because where the Earth would have been in the past, so they have to shoot them like, out in space like where the Earth was. And then because they're tachyons, they're faster than light, they go back into the past somehow. That was a pretty good one. I think there's a sequel to it, although I haven't read it. I have it, but I don't know if I read it. There's this book, Children of Time. I haven't read it yet. I got that recently, but apparently that one's really good. And then The End of Eternity. If you like Asimov, this is a really good one. Some people speculate that it's in the universe of the Foundation series. And, like the robots, Foundation, that whole, I don't know if you want to call that a series necessarily, but, they're all interrelated if you've read them. And some people argue that this is in that universe, although I feel like they're just trying to make it that way because it doesn't really cleanly fit in. But it is pretty cool. It's like these elite have time travel where they can go and influence the past. Yeah, the Eternals, the ruling class of the future. And it's pretty good. It's pretty good. I think it was one of the first Asimov books that I read. I didn't even realize it. I just read it and then later started reading more of his stuff. It says I purchased it in 2022. Well, okay, I take that back. I had read Foundation many, many years ago, but I didn't get it. So it wasn't until more recently when I started reading them again that I was like appreciating them. But that one's a really good one. This is also a really good one, The Accidental Time Machine by Joe Haldeman. He also wrote a book called The Forever War, which is pretty good. But I actually like this better. I don't really remember the plot very much. Struggling grad school dropout Matt Fuller is toiling as a lowly research assistant at MIT when he inadvertently creates a time machine. Yeah. This one's good too because you get these elements of like mysterious figures and you're not sure where they're coming from. It's very similar. There's a movie called Time Crimes, which is like that, where the whole time you're seeing these events kind of from one perspective, these characters, and you don't realize that they're, well, I don't want to spoil it if you're going to watch it, but it's like similar to Primer, where there will be events that happen in the movie and you don't realize till later, oh, that was these guys in the future coming back and interfering, and you didn't, it's like, okay, that's the cool thing about Primer. They developed this time machine, And they start going. They start like going in the past. Well, they get in the time machine. They no. How does it? They turn on the time machine. They get in, and then it takes them back to the past. That's what it is. And then they are doing it to be able to take information from the future, like stock market and stuff like that. But then they start trying to mess around with other stuff, like events in their life, family members, things like that. And it's such a cool movie because you could watch it 3 or 4 times and not realize the whole picture. There's parts of it that when I was watching it, I was confused by, and I just thought it was weird. And you don't realize like he's actually trying to tell you something with these like weird parts. And just watching, like, remember we watched a clip, I think on the live stream a while back, and like, well, I'm just gonna spoil it. I don't care if you haven't watched it. That's your fault. But there's this aspect where one of the guys is like putting her earpiece in so he can hear what's gonna happen next. He's like recorded it somehow. So he's already been through like this timeline multiple times, and he's like trying to stay ahead of the situation so he can like interfere and influence things. And I just remember now watching that scene where they invent the time machine, and the one guy's showing it to the other guy, and the guy's acting all surprised. But if you watch it very carefully, he's got that earpiece in his ear the whole time. And you're like, oh man. So there's so many scenes where you think you're watching the scene happening for the first time. And it's so complex because it's hard to know in each scene how many times this has already happened, which person already knows, and they're just acting, like they don't know. It's really, really good. It's like, it's not just good for showing the story. It's like almost like creating the experience through watching it of the confusion that's occurring and all of the kind of fucked up convolutedness that's occurring because of what they're doing, interfering with the different timelines. Like the movie kind of creates that experience within you while you're watching it. So anyways, that's a really good book. Or what were we talking about? Joe Haldeman, yeah, that one's good. Kind of weird. And then there was this Philip K. Dick book called The Martian Time Slip. And man, some of these Philip K. Dick books, you have to read them multiple times to understand what the hell's going on. But there's like a kid, and he's sort of autistic, like he's some kind of genetic freak or something. Yeah. Space travel causes genetic mutations and abnormal births. So they have these kids, and one of them is, oh, that's funny. Jack Bolan is a repairman who immigrated to Mars to flee from bouts of his schizophrenia. I don't remember that. That's interesting. So he was trying to escape from schizophrenia. And then there's this kid, anomalous child, who can basically see the future, and the guy tries to use it to invest in real estate. It's pretty funny. And then there was a few others. I just looked up, what are other Philip K. Dick novels about time travel? So there's Ubik. It's so weird, man. I would read these novels and then look back at the descriptions and be like, is that what it was about? A half-life world that is continuously degrading into the past, with characters using a product named Ubik to temporarily fix their reality. Part of the problem is it's like a somewhat schizophrenic person writing these novels, and then I'm also reading them like when it's like late at night going to sleep, so it's probably not the best way to read it. But I always like reading this. Now Wait for Last Year. I don't know if I've read that one. I don't think so. A powerful addictive drug called JJ-180 that allows users to travel through time and space, often leading to alternate realities. Sometimes, though, if I look further into it, I'll realize I did. I don't think so. I don't recognize those names. 2055, Earth is caught between two galactic powers in an interstellar conflict. Dr. Eric Sweetscent and his wife Kathy get addicted to a powerful drug that appears to cause time travel. The doctor's patient is the world leader UN Secretary General. Yeah, I definitely don't think I've read this one. Set during a war between the Starmen and the six-limbed insectoid creatures called the Reeks. Well, I don't want to spoil it for myself. I don't mind spoiling things for you guys, but I don't want to spoil it for myself, so I'll probably read that. I'm sure I have it. Counterclock World. I'm pretty sure I've read that one. Explores a world where time has begun moving backward, leading to the dead rising and people reversing their lives. Hobart Phase, causing people to be born old and grow younger. Can't really see if I've read that one or not. Dr. Futurity features a doctor kidnapped to a future where death is voluntary. Yes, I've definitely read that one. I think that was relatively recently I read that one. He's born in 1980, living in 2012. He goes to 2405. Oh, yeah. Yeah, okay. That one was pretty interesting. Okay, so that's a time travel one. The Variable Man, I definitely have not read that. The use of a time viewer to calculate probabilities in a war? Time Out of Joint. A faux time travel story where a man discovers his 1950s suburb is actually a manufactured reality created by future forces to exploit his precognitive abilities. Regal Gum. Yeah. I think I talked about this one before. So there's this newspaper game, like the crossword puzzle kind of thing in the newspaper called Where Will the Little Green Man Be Next? And so there's these people, like they play the newspaper game and they send in, it's like there's like a grid and you got to figure out where the green man's going to be next, and like you got to send in your answers and then you win prizes. And he's like won so many times. He like makes a good living off of it. And it turns out he was actually helping the government predict where missiles were going to land that were being fired from the moon. But he didn't know that. And it gets real weird. I mean, as all of these do. They're super easy to read. They're usually not very long as novels. Also, the way he writes dialogue. It's so hard to explain. I can't tell if it's unrealistic or realistic. Because if you were to write dialogue realistically, like how people actually talk to each other, it probably wouldn't be very interesting. So a lot of times when you read dialogue in a book, it's like people would never actually say these things, But the way he writes is kind of like in between. It's like they're usually like very short. I mean, not that people don't go on a monologue or something, but the way they talk to each other, it's like more realistic seeming. I was just thinking about this one book. And I can't remember what it was called. I'm pretty sure it was that one about the Glimming. What was that one called? Not Nick and the Glimming, because that's like the children's version of it. Galactic Pot Healer. There's this robot character that's hilarious. Galactic Pot Healer robot. Some of the dialogue in that is so funny. Willis. That's right. Okay. The robot says to Joe, "Everything is in my pamphlet." "Then you're a Colland," Joe said. The robot eyed him, long and carefully and silently. "And your pamphlet is the Book of the Collins." "Not exactly," the robot said at last. "Meaning what?" Molly demanded sharply. "Meaning that I have based my various pamphlets on the Book of the Collins." "Why?" Joe said. The robot hesitated and then said, I hope to be a freelance writer someday. Yeah, that's not really one of the funny ones, though. Let me see. Galactic Pot Healer. Robot. Willis, that's his name. Willis Lines. Oh yeah, this looks like one of the lines I was thinking of. Yeah, like this kind of stuff. Okay, so they're talking to the robot. A 3-room apartment is ready for you and Miss Yoja's, Willis said. Your personal living quarters. What? Joe said. A 3-room apartment. You mean we have an actual apartment, not just a room? A 3-room apartment, Willis repeated with robotic patience. Take us there, Joe said. No, Willis said. You have to say, Willis, take us there. He goes, Willis, take us there. Yes, Mr. Fernwright. They do that joke multiple times where, like, they'll be talking, and it's like you know the robot understands what they're saying, but he'll be like, no, you have to say, Willis, take us there. Let's see. Is there any more like that? It's so funny. There's not really more quotes about it. Oh well, you'll just have to read the book. It's pretty funny though. There will just be like these random sections where it's like really funny, and then but the book's not like funny overall. Let's see what else. Okay, I talked about that one. Okay, I'll come back to replay. Oh yeah, this book. This book is weird. The Man Who Folded Himself. And this guy, David Gerald, he wrote the script for the original Star Trek episode, The Trouble with Tribbles. The Martian Child was made into a movie? I don't know about that. The film, Martian Child. Never heard of that. John Cusack as a writer who adopts a strange young boy who believes himself to be from Mars. Have I seen this? 2007? No, I doubt it. David Gordon, a popular sci-fi author. They adopt a boy. He believes he's from Mars. Why does this feel familiar? What is that feeling? It's not deja vu and it's not nostalgia. It's like a mix of the two. When you feel like you've seen something before, but it's not deja vu. I'm going to ask ChatGPT. Is there a feeling that is a mix of deja vu and nostalgia? Deja vécu. No, that's not what I'm looking for. I don't feel like I've lived through that moment. And anemoia, nostalgia for a time you never experienced. Hey, it's kind of like a time travel type thing. Isn't that weird? What a coincidence. Saudade, a Portuguese word for longing mixed now. Yeah, uncanny. Maybe that's it. Something feels both familiar and strange at once. I don't know if I would say that totally fits that exactly, but liminal nostalgia. No. It feels deeply familiar, emotionally important, and distant, as if I've known or lived it before, even if I haven't. Mm, uh, say you're looking at a movie description and you feel like you've seen it, but you haven't. Is there a term for that? Deja vu mixed with anticipatory nostalgia. Pre-familiarity. That's what it is. It's probably a time travel situation. I've probably seen this movie in the future because of this, looking at it, and I'm remembering myself watching it in the future. That's probably what's going on. The brain kind of simulates the movie before you see it. I feel like he's just making this shit up because I said it. Deja rêvé. Already dreamed. Feel like something was encountered now. Cryptomnesia. When something feels strangely familiar without knowing why. Yeah, it's kind of like that. Semantic deja vu. Familiarity triggered by concepts or narrative structures rather than literal memory. Yeah, I don't know. Something about that. But it came out in 2007. And I'm just thinking, like, why would I have watched this movie? It just seems like something I've watched before. But I don't remember any of these details. The film is not based on David Gerrold's semi-autobiographical novel, The Martian Child, although it shares some of the incidents. Oh, okay. So he also has a semi-autobiographical novel called that, but he also has a novella called that. Got it. That'd be crazy. You adopted this kid, and they like really seem like they are from Mars, and you're not sure if they just believe it or if they really are. What would you do? They're like, yes, I have to eat Lucky Charms because what the hell? The sexuality of the protagonist is not disclosed, although the novel identifies him as gay. What does it do with anything? That makes sense, though, that David Gerrold was gay. Especially if you read The Man Who Folded Himself. If you do, you will understand exactly what I mean. It is a fucking weird book. It doesn't seem weird at first, but it gets real weird. Well, it kind of spoils it, but I'll leave it at that. It's definitely worth reading, though. It's one of those ones where, similar to like this book, for example, Recursion, also a really great book. This one, and then it's by Blake Crouch. He also wrote a book called Dark Matter. He's got other books too, but those two in particular, they're so intense. I don't really see how I can explain it without spoiling it. But like that infinity symbol it's got on there, I mean, that really sums it up. Dark Matter. Oh, I didn't even look what the other one's about. Oh well. Are you happy with your life? These are the last words Jason Dessen hears before his kidnapper knocks him unconscious. Before he awakens to find himself strapped to a gurney surrounded by strangers in hazmat suits. Before a man he's never met smiles down at him and says, "Welcome back, my friend." Yeah, they're not really, I don't remember which one's about time travel per se, but they both have a very similar theme to it. It's almost hard to remember which one is which. They kind of like meld together because I read them both very short, one right after the other basically. But they're super just like, yeah, mind bending. Both very good. I haven't read Upgrade, but I have that one. Okay, and then Replay. Also a really good novel. I really liked it. It's to call it sci-fi. Yeah, see, they call it a fantasy novel. I wouldn't really call it sci-fi because it doesn't really have very much like technological science type stuff, but it's definitely a time travel story. The novel tells of a 43-year-old man who dies and wakes back up in 1963 in his 18-year-old body. So basically, he wakes up, he's like back in college or whatever, but he remembers the fact that he had already lived his life, and he's like suddenly back in time. And at first, obviously, he thinks it's like a joke or what the hell's going on. And then he lives out his life, and then he dies and goes back again. But every time he goes back, it's like a little closer to the time that he died. And it's another one similar to that Recursion or Dark Matter or some of those, or even That Man Who Folded Himself, where it just it keeps looping and getting more and more intense. And that one's really good because he lives multiple different types of lives. He makes different decisions. Okay, you know what? I keep accumulating all this knowledge and information. Let me do something else this time. It's really good. Its time loop concept has been referenced as a precursor of Harold Ramis's comedy drama Groundhog Day. But it's not really like that movie at all. If you've watched Groundhog Day, which is an interesting movie, but it's not the same at all. Richard Lupoff explored a similar premise in his 1973 short story 1201. Science fiction author Damian Broderick credits the novel with introducing the replay trope, wherein time travel is often depicted without any kind of manufactured machine or technology as its source. Yeah, it's literally just replaying. A postmodern rejection of a universal meaning to life. Well, I don't want to spoil it, but it's really good. What is this 12:01 p.m. thing? Huh. I haven't read that one before. Okay, and then I saw this. Looking for recommendations on books with time travel. The Time Machine. Also very good is The Time Ships by Stephen Baxter. A sequel to The Time Machine. If that's any good. Oh, it's a link. Oh, it's 95? Okay. The Time Ships. The Time Ships. I wonder if it's any good. Hard science fiction. After the events related in Time Machine, the time traveler in 1891 prepares to return to the year 802,701. Save Weena, the Eloy who died in the fire with the Morlocks. Spoiler alert on the Time Machine. Huh. I wonder if it's actually good. It's got pretty decent ratings. Couldn't put it down once I started. Good job of adopting the tone and voice of the original. That's the only thing I didn't like about it, though. I don't know. Doesn't. It's always weird when they go 2,000 years in the future and they're still using computers with screens or something. You're like, yeah, right. What the hell? Okay. End of Eternity. The Time Patrol Stories by Poul Anderson. Huh. Poul Anderson's pretty good. I've read a few of his. Time Patrol series. Forget minor hazards like nuclear bombs. The discovery of time travel means that everything we know, anyone we know, might not only vanish but never even have existed. Ah, okay, so it's like police. They're like time police. Might be pretty good. There Will Be Time. What is this book? Soon after his birth in 1933, Jack Havig's parents experienced the first of many frightening incidents associated with their son. One day he seemed to appear double, disappear, and then reappear before his terrified mother's eyes. So he could travel through time. Looks pretty cool. I've read a couple of Poul Anderson's books. Not bad. Harry Harrison's The Stainless Steel Rat Saves the World. Technicolor Time Machine. A movie studio uses a time machine to shoot a movie about Vikings on location. Robert Heinlein's The Door into Summer. I've never heard of that. Huh. Let's check that out. Larry Niven's The Flight of the Horse, a collection of stories of a time traveler who goes into the past. I like Larry Niven. He wrote Ringworld, which is pretty good. Although most of the books I've liked is where he was like a co-author. Like Moat in God's Eye. There's that one about the aliens who like look like elephants. Can't remember what that one's called. The First 15 Lives of Harry August. This is how you lose the Time War? Okay. Seems like most people hate it. More of a romance and poetry in a sci-fi setting, not a sci-fi book. Alright. Seconding this one. Okay, some people like this. I've never... The First 15 Lives of Harry August. No matter what he does or what decisions he makes, when death comes, Harry always returns to where he began, a child with all the knowledge of a life he's already lived a dozen times before. Nothing ever changes. Seems interesting enough to warrant getting it. Okay. Somebody said The Man Who Folded Himself. Time and Again by Jack Finney. Never heard of that one. 1970 novel about a man who travels back in time to 1882 through a secret government project. Hmm. People really like that Claire North, and they actually like David Gerald one too. Gone World by Tom Sweeterlich. Oh, somebody said Hyperion Cantos. Wait, is there time travel? Oh yeah, the time tombs, duh. Kind of forgot about that. Dang, it's got a lot of ratings. Okay, Brilliant Crouch says to read it. Inception meets True Detective. A ship assumed to be lost. Oh, a spaceship, USS Libra. Huh. Sounds kind of cool. Dang, paperbacks. $20? That's kind of crazy that it would. When was it? When did it come out? It's pretty old. 2018? Huh. Is it like super long? Why is it $20? Brand new is $30? That's kind of crazy for just a paperback novel. 400 pages? Huh, weird. Maybe it's good. I wonder how they determine the prices on books. The Cross Time Engineer. Doesn't sound interesting to me. The Nantucket series by S.M. Sterling. Gets dropped back to the Bronze Age. S.M. Sterling wrote some of the Terminator novels. Rise and Fall of Dodo by Neil Stevenson. You know, I've never read that one. Oh, maybe that's why, because it's like a co-authored one. A secret U.S. government agency, the Department of Diachronic Operations, Dodo, that uses magic and time travel to alter history, blending science, history, and fantasy? What? Okay. I probably would have never read that otherwise. Looks pretty good. Dark matter isn't time travel. Yeah, it's like more about false memories or something. That's right. Wait, is that right? Yeah. It's like about. Well, I don't want to spoil it, but I think it's like about false memories. Okay, and then I got one more thing for you guys, which you might find pretty interesting. I remember watching this a while ago. 17 years old? That's crazy. But it's about imagining the 10th dimension. I thought it was pretty cool. Oh. Didn't realize you couldn't hear it. Hold on, give me 1 second. I hope you enjoyed the videos. Let's see. There we go. Now it should work.
We start with a point. Like the point we know from geometry, it has no size, no dimension. It's just an imaginary idea that indicates a position in a system. A second point, then, can be used to indicate a different position. But it, too, is of indeterminate size. To create the first dimension, all we need is a line joining any 2 points. A first-dimensional object has length only, no width or depth. If we now take our first-dimensional line and draw a second line crossing the first, we've entered the second dimension. The object we're representing now has a length and a width, but no depth. To help us with imagining the higher dimensions, we're going to represent our second-dimensional object as being created using a second line which branches off from the first. Now let's imagine a race of 2-dimensional creatures called flatlanders. What would it be like to be a flatlander living in their 2-dimensional world? A 2-dimensional creature would have only length and width, as if they were the royalty on an impossibly flat playing card. Picture this. A flatlander couldn't possibly have a digestive tract because the pipe from their mouth to their bottom would divide them into 2 pieces.
That's actually kind of interesting. They literally couldn't, because there's no third dimension for that to stay like an actual. You can't have a hole that is connected from one side to the other.
Possibly have a digestive tract because the pipe from their mouth to their bottom would divide them into 2 pieces. And a flatlander trying to view our 3-dimensional world would only be able to perceive shapes in 2-dimensional cross-sections. A balloon, for instance, would start as a tiny dot, become a hollow circle which inexplicably grows to a certain size, then shrinks back to a dot before popping out of existence. And we 3-dimensional human beings would seem very strange indeed to a flatlander. Imagining the third dimension is the easiest for us because every moment of our lives, that's what we're in. A 3-dimensional object has length, width, and height. But here's another way to describe the third dimension. If we imagine an ant walking across a newspaper which is lying on a table, we can pretend that the ant is a flatlander, walking along on a flat 2-dimensional newspaper world. If that paper is now folded in the middle, we create a way for our flatlander ant to magically disappear from one position in his 2-dimensional world and be instantly transported to another. We can imagine that we did this by taking a 2-dimensional object and folding it through the dimension above, which is our third dimension. Once again, it'll be more convenient for us as we imagine the higher dimensions if we can think of the third dimension in this way. The third dimension is what you fold through to jump from one point to another in the dimension below.
What? Okay.
Okay, the first 3 dimensions.
So the third dimension is a fold, is the point. Okay.
Dimensions can be described with these words: length, width, and depth. What word can we assign to the fourth dimension? One answer would be duration. If we think of ourselves as we were 1 minute ago, and then imagine ourselves as we are at this moment, the line we could draw from the 1 minute ago version to the right now version would be a line in the fourth dimension. If you were to see your body in the fourth dimension, you'd be like a long undulating snake, with your embryonic self at one end and your deceased self at the other. But because
a snake, huh? Maybe like the serpent. Yeah, that'd be pretty weird to look at. Like when God sees people, he sees them as like these weird long everything looks like that. Can you even imagine how that would look? How reality would look to God? It would be this weird fucking looking object. It would be real weird. Like everything, every particle would all be like all drawn out and like weird looking.
As we live from moment to moment in the third dimension, we're like our second dimensional flatlanders. Just like that flatlander who could only see two-dimensional cross-sections of objects from the dimension above, we, as three-dimensional creatures, can only see three-dimensional cross-sections of our fourth-dimensional self. One of the most intriguing aspects of there being one dimension stacked on another is that down here in the dimensions below, we can be unaware of our motion in the dimensions above. Here's a simple example. If we make a Mobius strip, take a long strip of paper, add one twist to it and tape the ends together, and draw a line down the length of it, our line will eventually be on both sides of the paper before it meets back with itself. It appears, somewhat amazingly, that the strip has only one side, so it must be a representation of a two-dimensional object. And this means that a two-dimensional flatlander, traveling down the line we just drew, would end up back where they started without ever feeling like they had left the second dimension. In reality, they would be looping and twisting in the third dimension, even though to them it felt like they were traveling in a straight line. The fourth dimension, time, feels like a straight line to us, moving from the past to the future. But that straight line in the fourth dimension is, like the Mobius strip, actually twisting and turning in the dimension above. So the long undulating snake that is us will feel like it is moving in a straight line in the fourth dimension, but there will actually be, in the fifth dimension, a multitude of paths that we could branch to at any given moment. Those branches will be influenced by our own choice, chance, and the actions of others. Quantum physics tells us that the subatomic particles that make up our world are collapsed from waves of probability simply by the act of observation. In the picture we are drawing for ourselves here, we can now start to see how each of us are collapsing the indeterminate wave of probable futures contained in the fifth dimension into the fourth dimensional line that we are experiencing as time. What if you wanted to go back into your own childhood and visit yourself? We can imagine folding the fourth dimension through the fifth, jumping back through time and space to get there. But what if you wanted to get to the world where, for example, you had created a great invention as a child that by now had made you famous and rich? We can imagine our fourth dimensional selves branching out from our current moment into the fifth dimension. But no matter where you go from here, the great child inventor timeline is not one of the available options in your current version of time. You can't get there from here, no matter how much choice, chance, and the actions of others become involved. There are only two ways you could get to that world. One would be to travel back in time, somehow trigger the events that caused you to come up with your invention, then travel forward in the fifth dimension to see one of the possible new worlds that might have resulted. But that would be taking the long way. The shortcut we could take would involve us folding the fifth dimension through the sixth dimension, which allows us to instantly jump from our current position to a different fifth dimensional line.
Makes it sound pretty easy.
In our description of the fourth dimension, we imagine taking the dimension below and conceiving of it as a single point. The fourth dimension is a line which can join the universe as it was 1 minute ago to the universe as it is right now. Or, in the biggest picture possible, we could say that the fourth dimension is a line which joins the Big Bang to one of the possible endings of our universe. Now, as we enter the seventh dimension, we're about to imagine a line which treats the entire sixth dimension as if it were a single point. To do that, we have to imagine all the possible timelines, which could have started from our Big Bang, joined to all the possible endings for our universe, a concept which we often refer to as infinity, and treat them all as a single point. So for us, a point in the seventh dimension would be infinity. All possible timelines, which could have or will have occurred from our Big Bang. When we describe infinity as being a point in the seventh dimension, we're only imagining part of the picture. If we're drawing a seventh dimensional line, we need to be able to imagine what a different point in the seventh dimension is going to be, because that's what our line is going to be joined to. But how can there be anything more than infinity? The answer is, there can be other completely different infinities created through initial conditions which are different from our own Big Bang. Different initial conditions will create different universes, where the basic physical laws such as gravity or the speed of light are not the same as ours. And the resulting branching timelines from that universe's beginning to all its possible endings will create an infinity which is completely separate from the one which is associated with our own universe. So the line we draw in the seventh dimension will join one of those infinities to another. And as boggling as the magnitude of what we're exploring here might be, if we were to branch off from that seventh dimensional line to draw a line to yet another infinity, we'd then be entering the eighth dimension. As we've explored already, we can jump from one point in any dimension to another simply by folding it through the dimension above. If our ant on the newspaper were a two-dimensional flatlander, then folding his two-dimensional world through the third dimension would allow him to magically disappear from one location and appear in a different one. As we're now imagining the ninth dimension, the same rules would apply. If we were to be able to instantaneously jump from one eighth dimensional line to another, it would be because we're able to fold through the ninth dimension. Before we discuss the first dimension, we could say that we first started out with dimension 0, which is the geometrical concept of the point. A point indicates a location in a system, and each point is of indeterminate size. The first dimension then takes two of these points and joins them with a line. When we imagined the fourth dimension, it was as if we were treating the entirety of three-dimensional space in a particular state as a single point, and drawing a fourth-dimensional line to another point, representing space as it is in a different state. We often refer to the line we have just drawn as time. Then, in the seventh dimension, we treated all of the possible timelines which could be generated from our Big Bang as if this were a single point, and imagine drawing a line to a point representing all the possible timelines for a completely different universe. Now, as we enter the 10th dimension, we have to imagine all the possible branches for all the possible timelines of all the possible universes and treat that as a single point in the 10th dimension. So far, so good. But this is where we hit a roadblock. If we're going to imagine the 10th dimension as continuing the cycle and being a line, then we're going to have to imagine a different point that we can draw that line to. But there's no place left to go. By the time we have imagined all possible timelines for all possible universes as being a single point in the 10th dimension, it appears that our journey is done. In string theory, physicists tell us that superstrings vibrating in the 10th dimension are what create the subatomic particles which make up our universe, and all of the other possible universes as well. In other words, all possibilities are contained within the 10th dimension, which would appear to be the concept we have just built for ourselves, as we imagined the 10 dimensions built one upon another.
That was interesting. You know what I was thinking might be interesting? Not tonight, but maybe another night. Just thinking of some ideas for future live streams. Number theory. That might be fun. Prime numbers, rational numbers. That could be pretty fun. Also, there's a concept called abstract algebra, which might be fun to go into. Yeah. King Osher is a little bit beyond some of this rudimentary string theory stuff they're talking about. Abstract algebra could be interesting too. Yeah, maybe I'll leave this up here so I can remember for tomorrow. I think that'd be fun. Let me see.
I'm a Bullis student tutor, and in this video I'm going to be talking about number theory. I'll be giving a brief introduction to what this is. Number theory is also called higher arithmetic, and it is essentially a study of mathematical interactions and number types. So we have a lot of different types of numbers. We've got odds, evens, squares, integers, rational numbers, all sorts of types of numbers. And what the branch of mathematics known as number theory does is take those types of numbers and ask questions about their relationships. And they use formal mathematical proofs to answer these questions. So let's give an example of one of these questions. About 2,000 years ago, a guy called Euclid looked at the group of numbers known as primes. And we should be familiar with what primes are. They're numbers that are only divisible by 1 and themselves. So some examples are 2, 3, 5, 7, and the list goes on. And Euclid, being a number theorist, looked at this group of numbers and asked a question. He said, how many primes are there? And his
It's an interesting question. You might think, well, obviously there's an infinite number, but maybe. You could actually prove it.
guess was that they were infinite primes, that no matter how far you went in numbers, no matter how high the numbers went, there would always be new primes. And so then he took that hypothesis and he proved it using a formal proof. And he used proof by contradiction, which is a type
It's actually pretty interesting how he does this.
of formal mathematical
See if
proof
he
in
shows
which
it.
he made the assumption that there were only a finite number of primes, and then showed why that assumption was wrong. So we can see that at its base, number theory is
Okay, let's think about it for a second. If you assume that there was a finite number of primes, if you assume there was a finite number of primes, you could take all of those primes I'm thinking he probably let's see, Euclid's proof, infinite primes. You multiply them all together and you add something. Yeah, exactly. So consider any finite list. So that means it's a finite number. You can write them all down. It might take a really long time, but you could write them all down and you'd eventually stop. You'd have them all listed out. So then he says, now multiply them all together. And that gives you a number p. Take that number, add 1 to it, and call that q. If q is prime, there's at least one prime that's not on the list. So that means you must have missed one. So it can't be because you already wrote them all down if they're finite. If q is not prime, then some prime factor p divides q. If this factor p were in our list, then it would also divide the big number p. If p divides p and q, then q must also divide the difference of the two numbers. Huh. That's interesting. if P divides P and Q, then P must also divide the difference? Why is that the case? Hold on. P must also divide the difference of the two numbers? Why is that? Wait, if Q is not prime, then some prime factor P divides Q. Q is P plus 1. I mean, that makes sense. If it's not prime, that means one of the primes has to divide it. So that makes sense why, if P was in the list, it would have to divide P if P is prime. No, sorry, wait, what did it say? If this factor P were in our list, yeah, obviously, because that's how you got big P in the first place, capital P, because it was the product of all the prime numbers. Okay. So if Q is not prime, then some prime factor P divides Q. Q being the P plus 1. That makes sense. But I don't understand this part. It would also divide, if P divides P and Q, then P must also divide the difference. Where are they getting that from? In general, for any integers a, b, c, maybe that's just common sense, but I never thought about it. If a divides b and a divides c, then a divides the difference. Okay, so like 6 goes into 18, 6 goes into 24, 24 minus 18, okay. Okay, that actually makes sense. Because if a number divides into two different numbers, then those two numbers must be multiples of that number. So there would have to be some multiple of that number in the difference as well. So that makes sense. That's just a basic property of divisibility. Interesting. Okay. Where'd it go? So, if P divides P and Q, has to divide into the capital P because it's the product of the primes. And if we're assuming that Q, which is this product plus 1, is not prime, is not prime, then it must also be divisible by one of the primes. So it also has to divide the difference. But the difference between Q and capital P is only 1, because Q is P plus 1. Since no prime number divides 1, P cannot be in the list. So therefore, at least one more prime number exists that is not on the list. So it just means that that P plus 1 has to be prime. The Q has to be prime. Fascinating.
Really all about asking questions about numbers. And for a long time, people thought that number theory couldn't be applied to the real world, that it was really just for the people who loved math and wanted to ask questions about math. But now, as we enter the 20th century, 21st century, we realize that number theory has a lot of real-world applications. One of the major tenets of number theory is the fundamental theorem of arithmetic, that basically says at its essence that all numbers can be factored into a unique set of primes. And we can see that using a quick example. If we take the number 12, we can break that up into 6 and 2, we know, and we see that 2 is a prime number. And then we can break 6 into 3 and 2. Those are its factors. And we see that 3 and 2 are also prime numbers. So the number 12 has a unique prime factorization of 3, 2, and 2. Those are its prime factors. And no other number will have those prime factors. So beginning in the 20th century,
It's kind of like a fingerprint for the number 12.
and especially now in the 21st century, number theory, and specifically the fundamental theorem of arithmetic, is being used for encryption schemes for large-scale business networks. A lot of times now, a business's computer network will be encrypted using prime factorizations. The key to their network will be a factorization of a huge number. And so that unique prime factorization for that huge number is the key to the business's network. So we see that number theory is about asking questions about math and using formal proofs to answer them. And we know that in the real world, you can apply these concepts to solve technological problems.
That's actually kind of interesting. Each number has a set of unique factors. And if it's a really, really big number, then that's going to be hard to figure out what those factors are, is what I'm assuming. So you could see why it'd be a problem if you could easily factor very large prime numbers, because then you could break all the encryption on all the computers. I don't want to do this new scientist one's probably going to copyright my video. Do a copyright claim, maybe, I don't know. Number rings.
There's a very real sense in which 5 isn't a prime number, because you can write it as 2 plus I times 2 minus I.
Of course, right? But that is interesting. I is the square root of -1. If you were to multiply that out, you get 2 times 2 is 4. You get 2 times negative I is negative 2I. 2 times I is 2I. And 2I minus 2I is 0. And then I times negative I would be negative 1 or plus 1. So you get 4 plus 1 is 5. Huh.
You can write it as a product of two numbers, other than just 1 times 5. This reveals something very interesting. Whether something is prime depends on the universe of numbers you're living in. What's happening visually is the following. Normally we work over the integers, that's the number line. Now we're working in a lattice in the complex plane, consisting of all complex numbers with integer coordinates.
So basically you've got on this horizontal number line all the integers, 1, 2, 3, 4, etc., and the negatives. And on the y-axis, the vertical one, you have all of the integer multiples of I. So 1i, 2i, 3i, etc. So you can think of any number in the complex plane as one of these points. So it has a real part and a complex part. So like the number 1, its complex part is 0. So it's just 1 plus 0i. But like that number we were just looking at with 5, it had 2 plus I. That would be, if you go on the horizontal, if you go over to 2 and you go up 1, well, well, you can't see my cursor, but if you go over 2 on the horizontal and up 1 on the vertical, that point right there is the number 2 plus I. Because normally you would have like a point, you'd have like, something, comma, something, but when you do it in the complex plane, you don't put a comma between the two, you just put a plus sign. So that point would be 2 plus I.
You can write 5 as 2 plus I over here,
Exactly.
times 2 minus I over here. So in this number system, 5 isn't prime. Our basic question in this video is as follows.
So are there any prime numbers in this?
How do the rules of number theory change when you extend your universe of numbers beyond the integers? The field of math that deals with this question is called algebraic number theory. In this video, we'll first introduce the basic concepts of the subject. This will allow us to enter one of the most beautiful branches of the theory of numbers, called Iwasawa theory.
Oh,
This is the branch of math that does number theory in infinite towers. The culmination of this video
didn't you ever want to do number theory in infinite towers, guys?
is the foundational result of this subject, which very
Well, what the hell is that?
loosely describes how numbers factor into primes as you climb the layers of a certain infinite tower. It's honestly one of the most beautiful theorems in number theory. Before we start, I'd like to introduce some helpful terminology. This number system that we saw is called Z
I said I wasn't going to do this tonight, but it's just so interesting to me.
adjoin I. It's the set of all complex numbers a plus bi such that a and b are integers.
So that's just describing, it's some mathematical notation, but it's just describing all the numbers on this plane, all the possible points.
This is an example of something called a number ring. A number ring is a universe of numbers like the integers. Now, I'm not going to give a precise definition in this video, so the viewpoint we're taking is you know it when you see it. The main theme when studying number systems like these is that many things that we take for granted over the integers aren't true over number rings. We saw one example.
See, and it's actually kind of cool. Depending on the perspective you're coming from, certain things are not necessarily true that you assumed to be true before. An example would be, if you add 3 plus 2, you get 5. If you reverse it and you put 2 plus 3, you also get 5. That's called commutation, right? When you can reverse the order of the numbers in the operation and you still get the same answer. But that doesn't work with subtraction. Subtraction is not commutative. If you do 3 minus 2, that's 1. But if you do 2 minus 3, you get negative 1. So even though it works in addition, it doesn't work in subtraction. But if you do instead 3 plus, and this is why, because minus is actually not a real, well, I don't say it's not real. It's not what you think it is. When you say 3 minus 2, what you're really saying is 3 plus negative 1. And when you do plus, it's commutative. So 3 plus negative 1 is 2. And if you do negative 1 plus 3, it's also 2. So the reason why it doesn't work with subtraction is because it's like you're hiding the negative number in the subtraction operation.
Example, 5 is no longer a prime. Another one which is more serious. Over the integers, it's a fact that every number can be factored uniquely as a product of prime numbers. This is often called the fundamental theorem of arithmetic because it's just so important. This fails quite spectacularly in
That's crazy because it's like, yeah, okay, so that's obviously true. And then somebody was like, but is it?
other number systems. For example, consider the ring Z adjoin the square root of minus 5, the set of all complex numbers a plus b root minus 5, where a and b are integers.
Okay.
You can
Which is like, okay, so it's similar to the other one. It's just instead of the square root of negative 1, we're doing square root of negative 5.
factor the number 6 in two ways. On one hand, you can write it as 2 times 3, but you can also write it as 1 plus the square root of minus 5 times 1 minus the square root of minus 5. So 6 factors as a product of primes in two different ways. Likewise, the number 21 factors into primes in two different ways. 3 times 7 and 4 times root minus 5 times 4 minus root minus 5. I want to stress, the problem here isn't that you can't factor numbers into primes. You totally can. Rather, you can't do so uniquely. This somehow suggests that looking at numbers and factoring them into prime numbers isn't the right way to look at things. The starting insight of algebraic number theory is, instead of looking at a single number, look at the set of all multiples of that number at the same time. As an example, consider the equation 2 times 3 equals 6. So instead of looking at the number 2, look at the set of all multiples of 2 at the same time. Instead of looking at...
Wait. Okay. It's like 2, 4, 6, etc. Okay.
the number 3, look at the set of all multiples of...
Like 0, 3, 6, 9, etc. Okay.
3. Now if you multiply all the numbers here with all the numbers here in all possible combinations, you get this.
What? I feel like maybe it's just the picture's not big enough. Like 2 times 3, okay. Maybe you would also get a 12, and you'd also get a 36, and you'd also get a, what is this, a negative 4? You'd also get a negative 24, okay.
Notice that the thing at the bottom is the set of all multiples of 6. This allows us to...
Right. Okay, that makes sense. Because you get 2 times 3, 2 times 6, 4 times 3, 4 times 6, and 4 times 3 is 12, which is a multiple of 6, 6 times 6, etc., etc. Okay.
to interpret 2 times 3 equals 6 in a different way. If you take all the numbers here, and you multiply them by all the numbers here, you end up with all the multiples of 6. Now, over the integers, I agree that this is a totally bizarre way to look at things, but this perspective is crucial to how we're going to think about multiplication in higher number systems. To see how it generalizes, we'll look at the properties of this set and make it into a definition. Notice that it satisfies these properties. First, it contains 0. Second, it's closed under addition and multiplication. If you add or subtract any two multiples of 2, the result is a multiple of 2. It is closed under taking multiples. If you have a multiple of 2, and you multiply it by any integer, the result is a multiple of 2.
When they say closed, they mean, like closed under addition means, he said it, but I'll just explain more clearly. It just means, like closed under addition means if I have any two numbers in a particular set, and I add them together, I'm going to get a number. So that's what it means to be closed. It means for like the set to be closed. So if I'm saying all the integers are closed under addition, means if I take any two integers and I add them, then I'm going to get another integer. So therefore it's closed under addition, meaning you don't get something outside of the original set. The integers are not closed under division though. Like if you take any two random integers, not necessarily any two random ones, but I could find two integers that if you divide them, you don't get an integer, like 2 and 3. If I divide 2 divided by 3, that's 2/3, that's not an integer. So the integers are not closed under division, but they are closed under addition and subtraction. He said also multiplication, he didn't put it there, but they would also be closed under multiplication.
This motivates the following definition. If R is any number ring, an ideal is a subset I of R that satisfies these three same properties. First, I contains 0. Second, I is closed under addition and multiplication. And third, if X is an I, then R times X is an I, for all R in the ring R.
Okay. So an ideal is a subset of all the real numbers. Real numbers is integers, rational numbers like fractions, 2/3, etc. Irrational numbers like the square root of 5. But it wouldn't include complex numbers because those are not real. So anything with the square root of a negative number would not be considered. But an ideal is like a set of numbers within the real numbers that contains 0, is closed under addition and subtraction, and if x is, if there's an element x in the ideal, then r times x is also in the ideal for any real number. Okay, so if the ideal, or if this set meets these criteria, it's considered an ideal. I'd never heard of this term before, and I got a degree in math, so I mean that should tell you something. But we definitely never studied algebraic number theory.
Again, when I first saw this, it made my head want to explode. So let me just say where this is going. Originally, given a number, we factored it into a product of prime numbers. Now, given an ideal, we will factor it as a product of so-called prime ideals.
Okay.
For the first, we saw that unique factorization isn't true. It's not true that every number is uniquely a product of prime numbers. The point is, for the bottom, unique factorization is true.
Okay.
Every ideal can be written uniquely as a product of prime ideals. That's the motivation for introducing ideals in the first place. First, let's give some examples of what ideals are. In the integers, the set of all multiples of 2 is an ideal. It's written 2 with brackets around it. For another example, let's look at z adjoin I. Consider the point 1 plus I, highlighted in red. Because an ideal is closed under addition, any ideal containing this point has to contain twice that number, and 0, and all integer multiples of that number. As well, it should also contain I times that number, which is this point over here, and then all integer multiples of that number. It should also contain all possible sums of these numbers. Filling in the gaps, you get this. This is the ideal written 1 plus I in brackets. It's the set of all multiples of 1 plus I. A word of warning, both examples that we've seen, the set of all multiples of 2 and the set of all multiples of 1 plus I, have been the set of all multiples of a single number. But it's not true in general that all ideals have to be of that form. For example, we looked at that ring z adjoin the square root of minus 5. It looks like this. Now consider these 2 points. What's the smallest ideal containing them? Well, if it
The smallest ideal containing them. Okay.
contains 3, it should contain all integer multiples of 3.
And if it contains, what is this, 1 plus I? No. Is that what that is? That dot's in a weird place. Oh no, that's the square root of 5. So I'd have to have all the multiples of that point as well. Okay.
If it contains 1 plus root minus 5, it should contain all integer multiples of that point. If you fill in the gaps, you get this. This is the ideal written 3, 1 plus root minus 5. The ideal generated by 3 and 1 plus root minus 5. Let's see how factoring into ideals as opposed to numbers fixes our older example. So we saw that you can factor 6 in 2 ways. But now, instead of factoring the number 6, let's factor the ideal 6. It factors as a product of 4 different prime ideals as follows. If you multiply the first 2, and then the second 2, you get 6 equals 2 times 3, our first factorization. And if you multiply them in a different order, you get our second factorization. So this whole time, these 2 factorizations weren't actually different. There was just a deeper underlying factorization into ideals, and we were just grouping the terms in different ways.
Weird.
This is confusing, so it's worth summarizing what we've seen so far. We've seen that certain number rings fail to have unique factorization into prime numbers. The fix was, instead of factoring numbers into prime numbers, factor ideals into prime ideals. And the way this fixes things is, whenever unique factorization into numbers happens to fail, there is always a deeper factorization into ideals that works. Now here's an interesting question. Given a number ring, how badly does unique factorization into prime numbers fail? This question will lead us to the punchline of this video. To answer this question, I'd like to introduce some helpful terminology. An ideal like this, that's generated by one number, is called a principal ideal. An ideal like this, that's generated by more than one number, is called a non-principal ideal. The point is, principal ideals are basically like numbers. You just write them with brackets around them. But non-principal ideals aren't like numbers. They're things that you add in order to restore unique factorization. So before we ask the question, given a number ring R, how badly does unique factorization fail? Now we can ask a more precise question. Given a number ring, how many non-principal ideals does it have? In other words, how many new ideals did you have to add in order to restore unique factorization? Now, as it stands, this is not a well-defined question, because a number ring could have infinitely many non-principal ideals. But there is a better way to quantify this. Consider these two prime ideals. It turns out that these ideals are scalar multiples of each other. In this case, that scalar happens to be 1 plus root minus 5 over 2. Likewise,
See, what's crazy about this is when he's writing it out, it's like, how the hell did you get that? Like, because it's just like their results already there. But somebody had to sit down and figure this out in the first place. It's not obvious. So, like, don't feel dumb if you're like, what? How'd you get that? Like, somebody sat down and was like, I don't know what it would be. Maybe there is one, and they had to figure it out. So that's part of the challenge when you're studying math is like, you'll get these results already given to you, and you're like, how the hell did someone come up with this? But it's like they might have spent a year trying to figure it out. Maybe not literally in this case, but they might have spent like a long time until they could figure out that exists, for example.
it turns out that this ideal on the right is also some constant alpha times the first ideal. In fact, every non-principal ideal in this ring is a scalar multiple of this one. This ring has infinitely many non-principal ideals, but they are all of the same kind, so to speak. They all address the same illness in the underlying ring. But that's not always true. Consider the ring Z adjoin root 82, which consists of all numbers a plus b root 82, where a and b are integers. Here, if you take these two ideals, then it turns out that they are not scalar multiples of each other. There is no
Interesting.
constant alpha that makes this equation hold true. They are genuinely different kinds of ideals. Likewise, with these two ideals, they aren't scalar multiples of each other either. So for this ring, you have to add in more than one kind of ideal in order to rescue unique factorization. To mentally organize this, let's do the following. Put all the principal ideals of this ring in a box. Then sort the remaining ideals based on whether they are scalar multiples of each other.
Why is that a principal ideal?
So this picture means all of the ideals living in the same box are scalar multiples of each other. This ring has 4 different kinds of ideals. To fix unique factorization, you had to apply 4 different band-aids. Compare that with the ring Z adjoin root minus 5. Here the picture is different. There are only 2 boxes, one for all the principal ideals and one for all the others.
Okay. At first I was like, how are those all principles? But, okay. Because I just didn't notice. In this blue box, for example, you've got 1 root 82, and then you've got 3 minus 5 root 82. But that's one number. Versus in the orange box, you've got 2 comma root 82. That's not one number. So in the blue box, everything in each set of parentheses is one number. It's just you can't write 3 minus 5 root 82 without the minus sign, but it's still one number. It's not like a pair of numbers. Okay.
Boxes, one for all the principal ideals and one for all the others, i.e. all the non-principal ideals are scalar multiples of each other. This ring has only 2 kinds of ideals. To fix unique factorization, you only have to apply 2 band-aids. Some terminology. The number of kinds of ideals in a number ring is called the class number of that ring. This ring has class number 2. This ring has class number 4. The class number answers our question: how many non-principal ideals did you have to add to recover unique factorization? It's a kind of proxy for how screwed up the underlying number system is. This ring has class number 2, so it's kind of screwed up, but not too much. This ring has class number 4, so it's much more screwed up than the first one. In general, class numbers can get very large. For example, If you look at z adjoin the square root of minus 3449, the class number is 100. There are 100 different kinds of ideals in this number system. It's very, very complicated. As another example, if you look at the number ring defined by this rather more complicated polynomial, the class number is 2000.
Jeez.
There are 2000 different kinds of ideals in this number system. But by far the most intricate number rings of all are these: z adjoin zeta n, where zeta n is an nth root of unity, the complex number sitting 1/nth of the way around the unit circle in the complex plane. This is the set of all complex numbers of the following form. They are a rich testing ground for understanding class numbers. To get a sense of how complicated these can get, here are some examples. For n equals 3, the class number is 1. For the next few values of n, it's still 1. Now let's see how it changes when n grows.
Wow.
As you can see, it explodes. And I want to emphasize, this is not for shock value. These numbers mean something very specific. As an example, in z adjoin the 23rd root of unity, the class number is 3. That means that this ring has 3 kinds of ideals. There are 3 different band-aids you need to apply in order to restore unique factorization in this ring. Now, if there's one thing I want to emphasize here, it's this. Nobody knows how to compute class numbers. They are very, very hard to calculate, even in specific examples. Because to calculate them, you essentially have to understand all the ideals in your number ring, which ideals are multiples of others and which ones aren't. It's a very complicated business. To underscore this, you might have noticed that in the previous example of a class number, it said GRH beside it. This means that this class number was calculated under the assumption of the generalized Riemann hypothesis, which is a very famous unsolved problem. In fact, even for the numbers that I showed here, most of these numbers are also conditional on the generalized Riemann hypothesis being true.
Wow.
The point here is that class numbers are very, very mysterious and nobody knows how to compute them. That all changed in the 1950s when Kenkichi Iwasawa entered the scene. Instead of calculating the class number of just one number ring, he actually looked at an infinite tower of number rings and calculated all of their class numbers in one shot. Specifically, he considered the following tower: z adjoin zeta p, z adjoin zeta p squared, z adjoin zeta p cubed, and so on for infinitely many layers. He noticed that if you looked at the class numbers in this tower, a pattern emerged. Take the case p equals 37. This is z adjoin zeta 37, z adjoin zeta 37 squared, 37 cubed, on and on forever. Finding the class numbers of these rings is very hard, but if you just look at the power of 37 appearing in the class number, you see an exponential curve. That is, the power of 37 appearing in the class number increases exponentially fast as you climb the layers of this tower. Take another prime, say p equals 11. So the tower now is z adjoin zeta 11, z adjoin zeta 11 squared, zeta 11 cubed, on and on forever. Let's look at the power of 11 appearing in the class number. Here, it's different. It's actually identically 0, i.e. 11 never divides the class number of any number ring in this tower. This kind of trend continues, so for some primes, like p equals 41, we see an exponential curve. The power of 41 dividing the class number increases exponentially. But for other primes, like p equals 5, it's a flat line. P never divides the class number of any layer in the tower. This is what Iwasawa was able to prove happens in general. His theorem was the following. The power of p dividing the class number of z adjoin zeta p to the n equals p to the lambda n plus nu for some integers lambda and nu. And this formula is true for every single value of n. The proof of this result is incredibly deep and difficult. It uses some very sophisticated tools.
Damn.
Group theory, representation theory, class field theory, and much more. The basic idea is that if you arrange these rings in an infinite tower, you can look at all of their ideals at once, and this object has many more algebraic symmetries than the ideals at any finite layer. This strategy was totally groundbreaking, and nobody had seen anything like it before. Unfortunately, the theorem as I've stated it, however, isn't quite correct. His result actually had an extra term, mu p to the n, for some integer mu. And unfortunately, this error term was absolutely gigantic. It was an exponential of an exponential, and it completely overshadowed the main term. To get a sense of scale, if you graph 2 to the 2 to the x, it explodes very fast. It almost looks like a completely vertical line. In numerical computations of these class numbers, Iwasawa noticed that for all primes less than 4009, mu was always equal to 0. That is, this term wasn't actually there. But it turned out to be very difficult to prove this for all primes p. And it took almost 30 years, and this was finally proved in 1979 by Ferrero and Washington. They proved that for all primes p, the mu invariant of the pth cyclotomic field was 0. But with this theorem in place, we could then remove this extra term and get the thing that we observed in all the data. That officially ends the math part of this video. I wanted to finish with a thank you. This channel recently hit 100k subscribers, and I wanted to thank you.
That was insane. And that's just some random question, is 5 a prime number? So maybe we won't go that crazy next time. Maybe we can look at some more basic stuff, but that was super fascinating. Again, it just makes you think about like all the knowledge and information that's out there. It's just crazy, actually. This looks pretty interesting. Maybe we can watch this another time. The story of information, from Morse to Shannon to entropy. I think that would be really interesting. Yeah, that'd be pretty cool. Information theory basics. That'd be cool too. I don't know, maybe we'll go back to some number theory in the future too, but there's a lot more basic stuff that's also very fascinating. That was just like insanely complex. Okay, we'll leave it at that for tonight. Hopefully that was fun, and I will see you guys tomorrow night, same time. All right, bye everybody.